Hi everyone. Welcome to our today's seminar. We are excited to be joined by Pastor Jackie, guest speaker, Professor Doni Masinde, and she's going to discuss about a prediction model for malaria using an ensemble of machine learning and hydrological drought indices. So about Professor, she is an established computer science researcher under South Africa's National Research Foundation, NRF for short, category C2 rating, as well as working as a professor and the head of the IT department at the Central University of Technology, Free State, South Africa. She is the founder and CEO of ITIKI, an acronym for Information Technology and Indigenous Knowledge with Intelligence. So Professor Masinde holds a BSc, MSc, and PhD degrees in computer science from the University of Nairobi, Kenya, the Free University of Brussels in Belgium, and the University of Cape Town in South Africa, respectively. She has also recently attained an MBA from the University of Free State in order to enhance her skills in running ITIKI as a business. You are most welcome, Prof, and over to you. So we'll just give you a moment to share our screen, and then we can start.
Thank you very much, Millicent. That's a generous introduction. I'm very delighted to be the host of the seminar today, the presenter of the seminar today. A few months just after we met virtually with you and your team. So I'll make my presentation, as you've said. The title is A Prediction Model for Malaria. Before I start, I'd like to acknowledge that this work is not done by myself alone. It's done in collaboration with a PhD student. She's Miss Paulina. And we work very closely with someone who works for the South African Weather Service as our chief scientist, Professor Joel. He's the one who reminds us when we make mistakes about climate and data. So for a start, this is a highlight. I'll give you some background and context of the presentation. I'll give you why we think there's a problem and how we set out to solve it with our objectives. We have a methodology which we followed and the results thereof. And finally, some discussions, conclusion, and further work. So for the background information, infectious diseases claim lives of many people. And from our research, and many of us know, we tend to have many of deaths happening in our continent for different reasons. One of them being an preparedness of our health systems. Most of the health systems that exist and try to address the challenges that face the health sector are still faced with multiple problems. For instance, there's an issue of accessibility, and for the context of today's presentation, we're looking at how can we foretell before it comes. In fact, if you do a search on funding applications and applications of IT and computer science, the area of health is very fertile. Many people are doing it. Many people are developing machine learning models to solve these challenges. So we are not doing something unique, but we got a little bit triggered by the newcomer, which we are calling the big climate data. Most of our research in the past, we were looking at prediction of droughts, and we thought, why not dive in and look, what is it that we can find to help address health challenges? Hence, this topic came up. So consequently, to prevent and control disease outbreaks, we do have several prediction tools out there, but we did not come across one that could address the malaria prediction way, the way we did it. So for us, then we came up with an hypothesis that if we can link infections to drought indices, that would help. And in my presentation, I will be justifying why drought indices, why not raw climate data or weather data for that in that case. So again, we also looked at why are we choosing malaria? Because we all know a lot of battles have been won about malaria. I want to crack a joke recently in December last year. One of my close family members, we had traveled to Nairobi and he fell sick with malaria. But you know, during the height of COVID, we didn't think it was malaria. So when we went to Nairobi hospital, we were 100% sure this guy has COVID. But what I'm trying to say is that the kind of medication already available is massive. You get tablets you drink 3 times once per day and you're okay. So the battle has really been won. But there's some reasons why we still think there's reason to do research in malaria. Interestingly, 93% of cases of people affected in malaria are in our continent. And not surprisingly, 50% of them are in that region. It's something to do with the latitude and the temperatures in the region of Nigeria, DRC, Uganda, you know, and the humidity that are in those areas. So 50% of the cases tend to be reported in that region. There are massive efforts. In fact, if you go to the World Health Organization website, you'll find a lot of material on malaria because this is something that people have paid attention to. And they have a global technical strategy to eradicate malaria by 2030. However, and it's a big however, there seem to be backward movement in terms of how much we've achieved the last 30 years because of climate change. Malaria is now being found in places where it never used to be found before. For instance, a year ago, malaria was reported in Cape Town, which has never been heard before. So this is being associated to climate change. And there's even research confirming that it might actually double by 2050. So there's still reason why we need to produce and generate these models that can predict incidences of malaria. Although we are focusing on South Africa, I need to report that malaria is not very common in South Africa. It's only common in Limpopo area, which is towards the north, again, for obvious reasons, the temperature and the position of the latitude thing I keep thinking about. It has something to do with it. Let me spend a minute or two to explain something about droughts. I've been doing my own research, like you had in the introduction. Itiki is actually a drought prediction tool that we've been developed back in between 2012 and 2013. So I've spent a lot of my life, apart from being computer science, I've spent time understanding droughts. There isn't one definition of a drought. Those of us who know right now, they're reporting that Europe is experiencing the worst drought since, I think, over 500 years. Drought just means, in very simple terms, there's not enough rain. But they do classify them to meteorological, which is the immediate one. There's not enough rain. The second one, the consequence of not enough rain, that's meteorological, not meteorological. Hydrological one is that the water levels in the water bodies suddenly drop, so it becomes a hydrological drought. The crops fail, it becomes agricultural drought, and consequently, the lack of everything, the food, the water, we end up with socio-economic drought. To measure drought in absolute numbers, we use drought indices, and the most common, there are very many of them, but I picked up SPI and EDI for the purpose of this presentation. And towards of my presentation, I'm providing some citations where more details can be found. Why do we use an index? So if I'm in the Free State right now and we say it only rained 10 millimeters of rainfall, and someone says in KZN towards Durban that it rained 500 millimeters, you cannot compare my 50 with their 500 because there's a level of expectation which we have. To give an example, in Kenya, if you look at in the Rift Valley, sorry, some echoes. Thank you. So we use an index because then I can say I have an index of 1, which will be the same. If someone in KZN says I have an index of 1 and I say I have an index of 1, you can compare those as opposed to comparing 500 millimeters with 500 millimeters. So I'm saying that because when it comes to training machine learning models, then it's easier to use figures that are standardized. So hence the choice of drought indices. In our research work, we prefer to use India because it's most of the indices tend to measure meteorological drought. But we would like to measure hydrological drought, which measures how much water is there in the ground, especially as a farmer. If it rained 5 days ago, how much water do I still have on the ground for me to be able to plant? So that's why we use India. And the good thing with India, apart from being a hydrological drought, it also gives us a value of available water index. I'll show you an example to explain this. This chart just compares the two main indices that I'm talking about. If someone says I have an index of 2, it means that there's a serious flood happening. So it's normally the number should be around 1. So if you have a -2, okay, sorry, is that a question? If it's a -2, it means extremely dry or severe drought is happening. So you can see these are values, they're standardized and they can be used to train the models, so to say. Sorry, that's a repetition on the slide. So these were the problems we were trying to solve in this research. Is there a correlation between hydrological drought? Because most of the studies tend to compare temperature and humidity. Although I didn't go into the details of malaria, we know that malaria is a parasite, is carried by a mosquito, and a mosquito needs a specific climatic region to thrive. That's why I was talking about the regions of Africa where you find malaria. It's something to do with how much humidity and temperature. The moment you go to down south, like Cape Town, the temperatures range goes too low that the mosquito cannot survive. So that's the simple explanation. Most models you read about, they tend to train the models using temperature and humidity. So this research wanted to check, do we get better results if you use hydrological drought? And that was the first question we were asking ourselves. Then we wanted to find out which of the machine model algorithms would give us the best results. And to that effect, then we wanted to see, can we then come up with a tool that we can install somewhere for people, for example, in whatever part of Africa, to predict if I know it's going to be this hot, it's going to have this humidity sometime in October, what are the probability that there will be malaria in that region? So that was our objective. Because we didn't have actual data from any other place, since we are based in South Africa, we focused on Limpopo province because that's the only province, and to some extent KwaZulu-Natal, that report any cases, significant cases of malaria. And at the end of the day, we hope that our model then can be used downscaled to lower levels, to a village level, and also upscaled so that we can use it in other parts of Africa. And just for contextualization, when we say an incidence, it means We measured the number of malaria cases per 1,000 number of people. Before we embarked on this research, we had also done similar models, but for the entire continent. It was an interesting because we collected data on the entire continent, and then we got temperatures for the entire continent, you know, but now if you ask me, if I say it's 10 degrees for South Africa, it's 15 degrees for Kenya, how realistic is that? But we just wanted to see, using those very high levels, how would the results be? So prior to the current work, we had already done this one for Africa. We had collected data from the World Health Organization website for the cases, where they just report how many people died in this country. And we also collected weather data, the one I'm talking about, rainfall and temperature. They kind of do have temperatures for Kenya, for Nigeria, for, you know, so we used it. And during that incident, we didn't want to spend too much time programming. So we used Rapid Miner. It's a free source software, which you can use. And within that software, you can actually train all manner of algorithms using different dimensions for checking computation. During that time, we got the results that were very interesting. Based on the classification, how long it's taking to classify. I mean, the classification type and the computational time. It came out that gradient boosted trees, random forest, decision trees, and deep learning were the main top performing algorithms in that order. At that time, we were hoping deep learning will be the best, but didn't. But all of us can guess. Deep learning, you need more massive data than we had. And then for algorithms like fast large margins performed very poorly. But still, and like I'll show you in a minute, the results were really interesting. And that's when we were motivated to go to the next level, downscale for South Africa. So the way Rapid Miner works is that at the end of the day, you get a very nicely, a tool with a user interface, because the 4 best performing variables that we came across was latitude, the temperature, rainfall, and longitude. So all you need to do if you want to predict, let me use, for example, we were trying to do one for Niger. So if you're in that country and you slide the latitude and also slide the temperature, then the number of cases you're predicting increases. And I can confirm that a temperature around between 25 and 26 degrees Celsius, I can't remember what the rainfall was, would lead to very high number of malaria cases for Niger, for example. So this result then informed us now to come down to South Africa and use the Limpopo data. So Limpopo, as you can see, is located very close to Mozambique, Botswana here. And the other place you'll find malaria in South Africa, I said, is KwaZulu-Natal, which is also not very far from Mozambique. In fact, they say most of the cases are carried across by people coming from Mozambique. But Limpopo has the highest number of malaria cases. In terms of rainfall data, so this is now the Limpopo, the extracted shape of Limpopo province. It has 5 administrative districts. So the one on top is Vembe district. Then you can see they have one which is called Waterberg and Mopani and so on and so forth. And then in terms of weather data, what South Africa Weather Service has done, it has divided the country into climate districts. So for instance, if we just look at Vembe district, within Vembe district, there are 2 climate districts. In other words, you can call them weather station, but they are not really weather station. It's an aggregation of a meteorological region. So we have 50 and 35, both of them are within Vembe district. And if you look at within Mopani district, administrative district again, you see the weather station, or let's call it weather station for now, districts, number 34 and 48. So essentially then we are on data points, data sources in terms of climate data, all these of them, 1, 2, 3, up to I think 14. And then the sources of malaria data was the administrative districts. For the malaria data, it was monthly instances reported. We got it from the Department of Health within the province for 1998 to 2019. And then for the rainfall data, this is basically rainfall, average rainfall data. We also were able to collect the temperature, the humidity, and so forth, but we did not use those. So we only used the rainfall data to calculate EDI. EDI, if you're interested, I'll also share the links to some of the papers we've published. It's very easy to calculate EDI because there's an elaborate formula. In fact, the first time we ever did this, we just wrote our own Java program to convert rainfall data to EDI. For every EDI value, it also generates for you the available water resource index. So I didn't mention earlier, one of the advantages of EDI as opposed to other drought indices is that with rainfall alone, you are going to go. You can generate the index. Let me give you a simple example of what the first time we ever used EDI. We were actually using, those of us who are listening from Kenya, we were using Kenya data from Kenya Met to calculate available water resource index. And interestingly, some of the floods that were happening quite a long time ago, 2002, if Kenya Met had used EDI, they could easily have been able to warn people in the low-lying areas the floods are coming, because what EDI gives you is, if it's raining 50 millimeters tonight, somewhere in the city of Nairobi, and the available water resource index for that area was very high. I mean, it's almost like the water table, the amount of water on the ground is massive. And that night it rained 50 millimeters, automatically it will be a flood. But if you only say it's going to rain 50 millimeters tonight, that doesn't tell you much. So, but if you combine those two, then you automatically give the hydrological element I was talking about. So then the 20-year data for training models, since we are data for 21 years, we use the 20 years for training, and then the 1 year for testing. The echo, sorry. Let me try to be louder to overcome the noise. So in a nutshell, if you look at, I know it might look a little bit small. So we had monthly malaria reported cases for all the districts, the ones I talked about, the administrative districts, starting with Capricorn all the way to Waterberg. And then we also had the precipitation data, monthly data, how much it rained in each of the climate districts. The one I was mentioning, 35, 48, and so on. Then we used that to calculate EDI values. You can see the negatives means a lot of drought was happening. And again, for all the months of the years that we had. And you can see here for each corresponding EDI value, we have an available water resource index, which means about how much water is available on the ground or in the atmosphere. So just to pictorially show you the malaria incident cases, as much as we're saying is in the entire province, it tends to happen at the district that are at the corner of border of towards the north of towards Botswana. So 2 districts account for most of the cases. That's Vembe district and Mopani district. But we also did a summation for the entire province to see the effect at that level. So for data processing, like I said, the normal feature reduction processes were carried out to ensure we have a data set that was usable. And we ranked the contribution of each of the values. Remember, now we end up with a lot of values for each district, because depending on the the proximity of the climate districts to the administrative district, there was a correlation. And as you would expect, the closer for this present, we call them rainforestation. The closer the rainforestation is to the particular administrative district, the higher the correlation. But what interested us was that the highest correlation was with the available water resource index. And that was exciting for us. It was our hypothesis, and it turned out to be a positive hypothesis. Just like we did with the case of Africa, the whole data set for Africa, in this case, we also used rapid minor. And because of the correlation types we came across, we only used the Vembe district, which has the highest, and we also used the cumulative total over the province. We had some interesting results, very exciting results. Why was it as exciting as it looks? The accuracy was very high, almost 100%. The error rate was very low. Classification error was very low. We were very excited. Recall 100%, so it was beautiful, and we could have gone to celebrate and party and gone to the Limpopo province and tell them, here is the tool you're going to use. However, as you can see also, the previous one, that one was for provincial level. The results were even better because when we moved down to the Vembe district level. And again, we didn't even need to choose any of the algorithms. They all did very well, except which is similar to the result we found for the continent data. The first large margin didn't really work for us. Of course, Paulina, doing her PhD, she went ahead and dived deep to find out why that was the case. So, and then later we ranked them in terms of which one was the best. But like I said, it really looked like all of them were very good, and any of them could have been used. But initially, our hypothesis, because it's influenced by where Paulina's PhD study was geared to, she would have wished that it was deep learning that was the best. And again, just like the simulator we did for the Africa level, we could simulate. The only difference now here, we are not talking about latitude and longitude. We are looking at the district, the rainfall district. And as you can see, most of the parameters that ended up being in our model are all available water resource index, which is the hydrological drought. Hence why we're saying, if you use hydrological drought, your indices for training malaria models, you are likely to get excellent results. So even though the Nation tree had a good performance during the training, it did not give good results. So when she came to the actual implementation of evaluating using the 1-year data, remember we had only 21 years of data. So we needed to test with the remaining 1 year. They didn't perform very well. But at least we managed to achieve our objective, that there's a very strong correlation between malaria and hydrological droughts for Limpopo. And that Nation tree malaria predictor system that was built can actually be used. But we really, like I will see in the conclusion, we really cannot give it to the Limpopo health department and say we can use it. And available resource index is conducive for malaria. In other words, why are we saying available water resource index is a predictor for malaria? Is simple. It's because the level at which the malaria vector, which is the mosquito, needs to thrive, you can measure it using hydrological drought. And the prediction capacity of malaria prediction system built in this study can be used by decision makers. So then what is the problem? The problem is that the small data set we had ended up creating overfitted models, and we could not carry them and use them in real life. So we've taken a few steps backwards to get bigger data set. For example, we might need to get data for at least 30 years, because those of us who might want or end up reading about NDI, NDI calculates an average of the drought value of a period of 30 years, then use it for the future. In other words, if I say that the drought index for, let's say, Johannesburg is 1, it's 1 for the 24th of August. It's based on the average over the different months of August for the last 30 years, because the amount of rainfall for August, for July, August, June is so different. So the fact that we use data that was for less than 30 years, that could be one of the, we're just speculating, that could be one of the reasons. The second reason, of course, is that we would like to get data on daily basis, because in DI, you can also calculate drought level for today, for tomorrow. So that's where we are. Then we hope with that bigger data set, then it will be possible to get models that are not being overtrained. We've also tried to make another many steps back and say, let's include the temperature. Let's also include the humidity. Let's look at vegetation indices. But the results that we've achieved, again, they are very high error rates, which means that this is still not the way. And the final thing we've tried to do is to receive data that matches the location. In other words, if you remember in my map, I was showing a weather station that is 500 kilometers from where the health center, which is receiving the malaria incidence, is. So we're trying to see, can we then use an actual weather station that is next door to where the malaria is being reported? And also other things that Paulina is pursuing is that we also need to find out if I'm reporting a malaria today, a case of malaria today, it doesn't mean that person fell sick today. It could mean that if you remember the cycle of the disease, it could mean that person was actually bitten by a mosquito 7 days ago. So if you're going to train the model using today incident with today's EDI indices, then the model is not correct. So there are a number of things you're doing. We may need to use 10 indices for 10 days ago and malaria incident of today, so that we can get the accurate values. So those are the things we are doing. We've achieved a number of results, but the moment we haven't published those yet, so we didn't want to present some of the results here. And lastly, and this is the uniqueness of our work, is that we are incorporating indigenous knowledge, because people in the village know if there are very many mangoes that have dropped under the tree and they are rotting, those mangoes provide very fertile grounds for the mosquitoes to breed. Also, when a mother brings a child to hospital, somehow they know, they already kind of know, almost 60% that, yeah, my child is actually suffering from malaria. So we've collected that indigenous knowledge, and we're incorporating with this, incorporating into these models, using things like VASI logic, VASI cognitive maps, and we are sure it will work, because for our drought prediction models, we're also using the same, so that before we tell them that there will be near normal rainfall that has been reported by South Africa Weather Service, we've also checked with the local people, the indigenous knowledge people. They are saying something slightly different. But from our knowledge, we know, from our research over 7 years, we know that in the short term, indigenous knowledge outperforms the modern science. So with that, then we'll be able to incorporate and deliver, hopefully, Paulina is working very hard, the tool by end of the year or latest June next year, that incorporate all those. And after that, then we can now go back and say, no, we can now interpolate it and take it to Mozambique, jump boundaries and take it to Kenya, hopefully. Some of the other things Paulina is trying out is to use ARIMA models for the same. She's receiving quite some good prediction results. This is continuation of the ARIMA model she's currently developing, a continuation of this. And you can see here the error rate is so bad. You know, you really can't use this to predict anything. As you can see, the predictor is giving values that are way beyond. the actual value. And lastly, the most exciting thing we're doing right now, we received over a year ago funding from Government of Flanders. So it's for 3 institutions, the South African Service, which is the host of the project, my university, the last one, which is the Central University of Technology, and then the University of KwaZulu-Natal. We are developing an integrated climate-driven multi-hazard warning system. And one of the things we'll be warning people about is malaria, droughts, floods, fires, and so on. And malaria luckily won't be plugged, our predictor won't be plugged in. So when we do release the entire system for the country, our predictor will be part of that system. I know I went over it pretty fast and in very high level, but that's what I wanted to share with you this afternoon and looking forward to the deliberation. The work I just presented is actually published in that paper. It was published last year and all the details are there. And also one of the other papers includes the results of the African level modeling of malaria. Thank you very much for your attention.
Thank you so much, Prof, for that wonderful presentation. If you have a question, please feel free to raise up your hand and then we'll just give you opportunity to ask it out. But we have a few on the chat. I'll read them for you, Prof. We have Alex asking, but you explained this, and I don't know whether you can talk about it again. Given the great results that you presented, the models are showing great results. Are there any risks of overfitting the models?
The last part of the question, I was trying to look for it. Are there what? Sorry?
Risks of overfitting the models?
Yes, of course. The moment the models overfit, they stop predicting. So when you overfit the models and then you use new data set, it gives errors. It doesn't work. It just stops, if you know what I mean. It freezes.
Yeah, cannot learn anything from any unseen data.
Yes.
Thank you. And another one, is there a hypothesis as to the reason why hydrological drought has a strong correlation? For example, movement of people from Mozambique in search of water.
And the first part of the question, the reason for the correlation between malaria and hydrological models, but I had the Mozambique part, so I didn't get it clearly.
Okay, he's saying, for example, movement of people from Mozambique in search of water.
Oh, I've seen it in the text. No, we need to isolate the movement of people. The movement of the people is something to do with, if I already have malaria, it means the plasmodium is in me, and I cross over to KwaZulu-Natal, and I'm bitten by mosquito while I'm in KwaZulu-Natal, then it's possible to transmit. So the movement is not linked to hydrological drought. But the hydrological drought is linked to malaria because of the amount of water there is. Remember, mosquitoes thrive in a place a bit wet. Yeah. So that's the link, yes. But the movement of the people is not linked to hydrological droughts.
Thank you. Jackie is asking a very interesting one because you mentioned about knowledge from indigenous. She's asking, how do you incorporate indigenous knowledge of people into your models?
Maybe that can be a discussion for another day. But what essentially we do, remember, indigenous knowledge are statements, if else, you know. So I'll give you an example. The one I was giving, if there are very many mangoes on the ground, and it has rained, then the cases of malaria are high. It sounds superficial. So what we do then, we use basic cognitive maps. It's a tool. In fact, they even have open source tools. So you build the weight. So you have to collect all the indigenous knowledge and build the weight for each, because the presence of mangoes on the ground and maybe the flowering of a particular tree, the mangoes part, it has a higher weight than the flowering of the tree. So you need to create that weighting system using basic cognitive maps. And then it's possible to convert those into numerical values. The moment they are on numerical values form, then you can incorporate them with indigenous data, with scientific data. But what you've done, because the one for malaria is still being cooked, is still in the oven, what you've done with the one for the rainfall is that using the cognitive map, you'll get a result that says it will rain on 13th of October for the October-November rain in Kenya. But then the Kenya Met is saying it will rain within the second week of October. You see, if I say this within the second week and the indigenous knowledge says on 13th, they more or less mean the same. So it's possible to combine those into one numerical value. So we do combine them, but using basic cognitive maps. I hope it was clear.
So I have another question, because then you have to be able to measure the number of mangoes on the ground. Because it's no good having that knowledge if you don't know how many mangoes are on the ground, which is a whole nother thing to measuring the amount of rain. So how are you proposing to do that?
One is that I will let you the predecessor process. What we do is that we have a mobile app. Okay, so we have a mobile app that takes images. Each champions, for our project, we do have champions. Each of the champions has a mobile app, so they take pictures, bring to the system, and use machine learning to interpret the images. For us, prior to this work, we developed learning to detect the quantity, by image recognition. At that time, we're doing it for the sky. So we're using from the sky, using the camera, and you learn through that. How thick is the cloud? Does that cloud to rain for tomorrow? And for to train our models, imagination to how the mangoes.
Sorry, Prof. We can't hear you. Your internet has suddenly become choppy. Maybe you could. Yeah, we can barely hear you. Maybe remove the video and put it back on. Maybe that makes a difference sometimes.
Is it any better, Vincent?
Marginally better, but at least now we can make us go on.
Oh no. But did you hear me when I was explaining about image recognition?
So up to the part where the villagers will probably have a tool where they take images and those are used then to, that's where I stopped. That's why I could hear.
Yeah.
Okay. For some of them, of course, we can't do for all the images. For some of the critical ones, we do use image recognition. And for this, we are piggybacking on a previous work that another PhD student did. In that case, he was using sky images to train the models to be able to tell, is this cloud for rain or is this cloud for no rain? So in the case of malaria prediction, we haven't thought about counting the mangoes, but what I can think from the top of my head, we may have to use image recognition if possible.
Okay, thank you. Do you have, I've had a look at your website, do you have any papers on the incorporation of Indigenous knowledge? Because we would love to read them if you do.
Yes, I will. In fact, maybe as we speak out, the recent one we published, they can paste the link. And luckily, it's in an open source. It's in an open journal. So yes, I'll provide the link, and you can download and check how we incorporating that.
Wonderful. Thank you so much.
Thank you for that. And we have another one from Cyrus. How can the problem of overfitting be alleviated depending on the available data for training? Why do you believe that 30 years of data would help with overfitting of the models? Basically working with what we have at hand.
Different things. One of them was to change the models we're using, but even then didn't help. So we're thinking getting more micro data will help. When I mean micro data, at the moment, it's just a simple calculation. If we have 21 years times 12, that's the only data we have. So the question is, what if we have 21 years times 365, which would be daily? We think that might help. But then we have a small challenge in the sense that how practical is it to calculate daily malaria incidences? So it's something we're still hypothesizing. I know Paulina was to be in this meeting. Paulina, if you're in and you wanted to add something else, that would help because she's the one who's pursuing all these options at the moment. I hope I helped.
Is she? She's not. I don't think she's in the call.
Okay, no, it's fine. It's fine.
Somebody want to just ask?
Well, one more. Mine was, you mentioned of an example of where, like an experience, you experience that indigenous models or indigenous knowledge really sort of does better than the scientific methods. And I was like, do you have like an example of that? And what would be your proposal? Like, how do we formalize the traditional knowledge, indigenous knowledge to be scientific? I don't know whether that statement makes sense, but yeah.
One of the reasons why indigenous knowledge tend to be accurate and only in the short term is because of localization. In other words, I'm talking about indigenous knowledge uses within 300 meters radius, If you look at the weather station that like the data we're using, it's very coarse. In other words, it's for 500 kilometers, or maybe that's an exaggeration, 500 kilometers. So the probability that that data represents me is very low. If I give you a practical example, we have one of the Kenya Met Geological Department weather station is in Embu town, a few kilometers on the upper side. That area has very different climatic zone compared to the lower side of Embu. So when someone tells you we are giving you forecast for Embu and using data that is collected in a place where even tea can grow, you cannot use that to the lower area where they never receive more than 500 meters of rainfall. So that's one of the reasons why it's more accurate. So when our predictor says it's going to rain on 13th of October, we are saying for a particular smaller location. So it's 100%. Okay, maybe not, but almost 100% correct. On the question of how do we formalize this, that's a big question. One of the things we've done, but we only did it for a subset of indigenous knowledge, observable one, the sky images, is to prove to someone that indigenous knowledge, prove it's correct in terms of if indigenous knowledge said it will rain and you can prove it rained, and publish that, more people would actually believe it. And most skeptics of indigenous knowledge, especially on weather, are the meteorological people, meteorologists themselves. So if you can prove to them that this is what indigenous knowledge said, and this is what you said from your data, which is the weather station data, there's a possibility we can prove it. It's a journey that we started. We want a publication where we have a scientific way of proving that IK is right. We just need more soldiers, maybe like you. Thank you.
Thank you, Prof. All right, thanks, Prof. One more. I'll just read comments from Mohammed. So he's suggesting using less data rather than training for fixed lag group time. That is, what is the expected indices rate given the previous 2 months over 2 years. So Mohammed is trying to make other suggestions here. And second, he's saying segmenting data so that you are considering local patterns for each area, that is use of data from a given area for predicting for the area. So just one more from Mohammed, another Mohammed. Have you explored using hydrological data collected from satellites?
Okay, no, thanks. I actually like the suggestions from Ment. He's right. One of the things we did, remember that initially we were using something like a black box, because when you use rapid miner, you don't have much control. So we moved from that. The current models we have, they have been we are not hard coding them. We are using Python. So we have better control now. We've trying to split data like suggesting. So I really welcome that. I'll copy, paste, and send it to Pauline because I consider this a forum also to learn. Thanks for that. We haven't considered satellite data for this project, but we are considering it for another project. In fact, one of the things we were doing was, we haven't implemented it yet, was first we need to compare the correlation between the satellite data and the rainfall station data. But no, I've read lots of work or people have done that. So it's something we're considering, but we haven't considered for this project. We're considering it for another one. We're doing crop production optimization. But again, I welcome that suggestion and we will consider it. Thank you very much.
Thank you so much as well. And I don't think we have any more questions, so we'll just end it at this point. Thank you so much, Prof, for the wonderful presentation and for sharing with us the material. Oh yeah, the internet is allowing us to say goodbye. So yeah, it was great, and we are super happy that you are able to create time and do the presentation. And please do share with us the slides and we will just forward it to our attendees. Otherwise, thank you and have a wonderful evening.
Thank you very much. Bye.
Thank you, Prof. Thank you everyone for attending.
Bye.